Thank you for joining us for today's webinar. My name is Jolie McGrath, the Distribution Coordinator at Thermtest, and I will be the host for today's webinar. Today we're presenting Measuring the Effects of Moisture Wicking Fabrics and Thermal Effusivity, presented by Jeff Ritalik and Benjamin Brooks. Before we begin the webinar, I would like to mention our upcoming 3 webinars. All attendees to this webinar will receive an email invitation for our upcoming webinars once registration is open. At the end of the webinar, questions will be answered by either Jeff or Benjamin with the remaining time. Please type your questions into the chat box at any time during the webinar. If we run out of time during the Q&A, remaining questions will be answered in the post-webinar email on Thursday, August 13th, along with a link to the recording. Presenting today will be Benjamin Brooks, the Chief Operating Officer at Bondmeyer Textiles, Inc., and Jeff Ritalik, the Junior Application Scientist at Thermtest. So I will pass along the webinar to Jeff now.
Okay, thank you, Jolie. Today we're going to be talking about thermal effusivity, the thermal effusivity meter developed by Thermtest, and then how we measure a moisture wicking fabric developed by Acticool. At the end, we'll be comparing 3 methods for measuring thermal effusivity, followed by a quick question and answer period. So to start, what is the TPS-EFF? Well, this is a portable effusivity meter developed by Thermtest. Beyond its competitive pricing, it is portable, so you can conduct your measurements anywhere using battery power, or you can plug it into the wall or the computer and use USB power. It's very easy to use as a user-friendly user interface, and there's a feature that allows you to automate your experiments. So you can set up a series of experiments, walk away, and come back when it's done. The effusivity meter is versatile with multiple ways of measuring a sample, and it complies with an internationally recognized standard of testing. So how does this meter work? Well, this is a transient plane source instrument. And like any transient method, it involves a heat pulse. So from the meter, a current is applied to the sensor. The sensor then heats up, and this heat diffuses one-dimensionally into the sample from the sensor. There's a temperature increase experienced by the sensor during this time, and the temperature increase over time is used to calculate thermal effusivity. There are multiple different ways to measure a sample. Typically, with small samples, you measure with the sensor facing upwards. Now, if your sample is too large to do this, or for any other reason, you can measure with the sensor face down. If you want to vary compression in your sample, for example, in the figure on the right, the TPS-EFF sensor is mounted in a compression stand with a piece of compressible foam on top. This allows you to vary compression over time or pressure. You can also vary temperature and other parameters over time if you wish. Viewing data on the TPS-EFF is very easy. The meter features an onboard display that allows you to view your measurements without using a computer. However, if you wish to use a computer, you can. The TPS-EFF comes with a data utility, and this can convert the data into a CSV file format that is compatible with Excel. So if you look on the left here, here's a heat graph of a measurement, so a temperature rise over time. And using the data utility software, the same heat graph can be seen in Excel. So what exactly are we measuring? What is thermal effusivity and what is thermal effusence? Most simply put, thermal effusivity is a number that you can attribute to a material that will indicate to you how warm or cold it feels to the touch. This allows you to compare different materials that are similar, and you can tailor your material to feel attractive to a buyer. Types of materials like this include flooring, automotive interiors, bedding, mattresses, clothing, coats, shoes, and so on. We will later on see how we measure a form of active wear developed by Acticool. Essentially, anything you can touch or that you come in contact with has a thermal effusivity value. So what is the difference between thermal effusivity and thermal effusence? Well, the prime difference involves the modes of heat transfer. In thermal effusivity, similar to thermal conductivity, the only mode of heat transfer involved is conduction. Conversely, thermal effusence involves not only conduction, but also convection and radiation. As thermal effusivity is commonly interchanged with thermal effusence, but we figured it would be very important to make that distinction now. So even, especially in textiles and fabrics, the proper term is often thermal effusence. However, most people just say thermal effusivity. So a bit more about thermal effusivity. It is not a standalone quantity, but it rather is an expression of other quantities. If you look at the equation here, thermal effusivity is equal to the square root of the product of the thermal conductivity, the density, and the heat capacity of the material. If we look at the graph closer to the middle of the screen, it features the temperature rise over time of a material with low thermal effusivity in red and high effusivity in blue. So the low effusivity material that is fairly insulating experiences a quicker temperature rise over time. The slope is steeper than its counterpart, which has a high thermal effusivity. It's important to note that since this meter uses short test times, thermal conductivity cannot be accurately determined from this equation. Here are a few more of the specifications about the TPS-EFF. You will notice that the TPS-EFF assumes one-dimensional heat transfer in its effusivity calculations. How can we ensure this? Well, if you use a large diameter sensor, then with short test times over a limited thermal effusivity range, you can ensure that the heat penetration, or the shape of the heat wave penetrating the material, is one-dimensional. So in the figure over here on the right, we have the TPS sensor and an arrow depicting the direction of heat transfer, which is perpendicular to the plane of the sensor. So how can we ensure this? What is the evidence that the heat is truly propagating one-dimensionally? We can verify this with an anisotropic sample, where anisotropic, if we start with isotropic means the material has the same properties no matter which direction you measure it in. And anisotropic means that that is not the case. So with this standard material with known properties, NIST 1450D, this is a fibrous glass board. It is known that heat propagates slowly through the thickness of this material and quickly radially. So if we perform a measurement on this material and the heat propagation is not one-dimensional, we will see that very easily, as any amount of heat loss in 3D will be exaggerated due to the properties of this material. If we use the known properties of the material and calculate the expected one-dimensional thermal effusivity, we get 67 watt square root seconds per meter squared Kelvin, or thermal effusivity units. If you compare this to the measured value of 63 effusivity units, we see that these values are very close, indicating a good correlation to one-dimensional heat transfer. You will also notice that the TPS-EFF features two different test times of 2 and 10 seconds. Why is this? This allows a simulation of a 2-second touch and a 10-second touch, where the longer test time allows the heat wave to penetrate further into the material. What is the advantage of that? Well, for layered or non-homogeneous materials, the effusivity value that you obtain is going to vary depending on the touch time. Some examples of this would be a tablecloth over a table, a fitted sheet on a mattress, a phase change material. For a short touch time, you're mainly getting a value indicative of the surface of the material, whereas using a longer touch time, you get a value that is more indicative of some of the deeper layers of this material. If we look on the right, we have a negative control, where we are measuring a mattress sample that is fairly uniform in composition. Whether we measure for 2 seconds or 10 seconds, the mattress is fairly insulating. It yields a low effusivity value. If we look on the left, we have a phase change material. So this is a material with a melting point that is slightly above room temperature. And then when the sensor or someone's hand touches this material, the heat from the material will not penetrate through the PCM. Rather, it will be involved with an endothermic reaction, changing the phase change material from solid to liquid as it melts. So as we take the measurements from 2 and 10 seconds, we see that the heat wave does not penetrate into the mattress. In fact, it increases, it does not decrease, indicating that most of the heat is being sucked into the phase change material. If you look at the middle figure, there's a layer of active material over top of the mattress. The active layer is designed to feel cold, and for a 2-second touch time that is mainly measuring the surface layer, it yields a value indicating that it does feel cold. However, for a longer touch time, for 10 seconds, we obtain a lower effusivity value indicating that the heat wave is penetrating further into the mattress. The TPS-EFF was designed to comply with a standard developed by the American Society of Testing and Materials. This is an internationally recognized institution that is depended on to ensure accurate and repeatable measurements. Without further ado, Ben is going to tell us about Acticool, a company that produces activewear fabric with exceptional cooling properties. Take it away, Ben.
Thank you to everyone for taking the time to join us. Acticool was initially developed as a base layer for use under body armor. The issue we initially set out to resolve was the moisture and humidity trapped against the user's skin, which causes rashes and discomfort. We did so by developing a multi-layered hydrophilic yarn, which pulls the humidity away from the skin on contact, and then disperses it across the fabric, slowly bringing it to the surface. In doing so, it creates a cooling effect, substantially dropping the wearer's surface temperature. In layman's terms, this means that as soon as you put on an Acticool shirt, it starts pulling away your sweat. Instead of drying super fast, the fabric moves the moisture around rather than leaving it in one spot. This helps get rid of the bubble of humidity between you and the shirt and stops that wet blanket feeling. In the last few years, the dangers of heat stress has become of greater concern. When we're exposed to heat, our bodies begin to thermoregulate. It tries to bring our core temperature back to equilibrium by increasing both the blood flow to the skin and sweat production. The issue is that as we perform physical labor, our bodies direct blood flow towards the muscles as they require increased levels of oxygen to stop up the buildup of lactic acid. The resulting decrease in blood flow to the skin will ultimately lead to the body storing more heat, and that raises your internal temperature. Now, one of the most recognized effects of heat stress is the loss of concentration and the ability to focus on the task at hand. Years ago, NASA developed the heat report CR12051, and it found that any temperature over 80 degrees Fahrenheit had a marked negative effect on both the productivity and accuracy of work. At about 95 degrees, the report showed that study participants were found to make 60 mistakes an hour, which really correlates to 1 mistake every minute. So whether you're in law enforcement, factory work, on the field, or on the ice, mistakes can be very costly. When we started this development, we initially tested the cooling phenomenon of our fabrics using thermal imaging. But as each user is different, we needed a more controlled method to determine the level of coolness of our fabrics. And that's why we turned to thermal effusivity testing, which shows not only how our fabrics really feel against the skin, but also how we measure up to other fabrics that are currently available. So at this point, I'll hand things back over to Jeff for more details on how we tested the Acticool.
So presented with this fabric that has cooling properties and is often encountering situations where moisture is involved, we wanted to set up the samples in accordance with the standard for testing textiles and fabrics, and to simulate sweat. Even though the composition of sweat varies from person to person, sweat is still primarily composed of water. So we chose water to simulate the moisture conditions. Here's a quick demonstration of sample setup, and it takes us all the way to sample measurement. So first we take a layer of Acticool fabric, and we moisten it. We then remove any loose water, and then we stack this fabric, staggering it between the other layers of fabric to prevent alignment between layers and ensure better repeatability of measurements. We then apply the stack of fabric, which is one sample, to the sensor, and a layer of Lexan to ensure there are no wrinkles in the sample. That is to ensure better repeatability of the measurements. And then we apply a mass to the sample to ensure good contact between the fabric and the sensor. And then after waiting a period of time for the sample and the sensor to reach isothermal conditions, we can perform our measurement. What we observed during this testing for these fabrics was that at a higher percent water saturation, the value of effusivity for the fabric was also higher. This means that as you get hotter and sweatier under these conditions, the fabric gives you an increased cooling effect proportionately to the amount of strain the user is undergoing. After observing this trend, we thought it would be interesting to compare how this trend in the Acticool fabric compares to a popular brand of athletic wear. Keeping in mind that standard operating conditions are typically at around 60% water saturation. What we found was that in the expected working range, Acticool outperformed the athletic wear in its ability to provide a sense of coolness and comfort under situations of strain and discomfort. And before we clue up, here's a slide indicating the correlation between three methods for measuring effusivity. We have the TPS-EFF meter, we have a TPS method, and a modified TPS method. The TPS meter uses a 10-second measurement and assumes one-dimensional heat propagation. The TPS method uses a 10-second measurement and three-dimensional heat propagation. And the modified transient plane source uses a 1-second measurement with 1D heat propagation. We tested three different materials across the effusivity range described by the ASTM standard. Starting on the left, we have EPS. This is an insulating foam. This is expanded polystyrene. In the middle range of effusivity, we have PVC, polyvinyl chloride. And on the upper range of the effusivity, the range of effusivity described by the standard, we have Pyrex. And so all of these materials have a known value. We then measured these values using the three different methods and compared the measured value to the known value using percentage difference. What was found was that the TPS-EFF had the lowest percentage difference from the known value for all three materials. So it obtained the most accurate value for all three materials. And with that, we would like to thank you for listening, and we would like to open up the floor for some questions.
the presentation. So I will now go ahead and read some questions that were submitted during the webinar. Just a reminder for those who had questions but didn't have a chance to ask yet, please be sure to type your questions into the question box in your control panel. As mentioned previously, questions that are not answered during the remaining time will be answered in the email for Thursday, August 13th. A link to the webinar recording will also be able to view. I'll just wait a few minutes for people to type in their questions, and then we'll go ahead and answer. So the first question, isn't Lexan stopping evaporation and changing the measurement compared to a wet shirt behavior?
Yes, it is. And we would like it to stop evaporation during measurements, as you need to take many measurements over time. We take 5 measurements and then average that value. What we do to allow the material to evaporate is we remove it from the sensor, and we remove the Lexan and the mass as well. So in between measurements, we do allow evaporation. That's how we get our curve that spans from 0% moisture saturation to 100.
All right, if there are any more questions, we can wait a few minutes. The second question was, what about graphene-coated fabrics?
As long as, I'm not sure exactly what the question is alluding to. Are you wondering if you can measure the effusivity of graphene-coated fabrics? Or is it how they behave when subjected to moisture?
He's asking that it might be far off from 1D behavior.
Yeah, depending on if you measure isotropic samples, as long as you cut a small sample and place it over the sensor, you should ensure one-dimensional heat propagation.
Great, thanks. So our next question is, how does density affect effusivity measurements?
If we look back to the effusivity expression, it is a square root relation. As density increases, that should increase the effusivity.
So we'll go with this. What is the thickness range of the samples that can be tested?
There is no limit to the thickness range. However, you do want to ensure that your sample is not too thin. It needs to be of sufficient thickness that the heat wave does not penetrate past the thickness of the material. There's a technique described in the user manual of the TPS-EFF on how to do this.
All right, and I think this will be our last question for the day, and then the rest, if there are any, will be answered in the email. So the last question is, which method is accurate out of the 3 different methods? Is it the TPS-EFF or MTPS or other?
Based on our correlation study at the end of the PowerPoint there, the accuracy of the TPS-EFF was better for these materials. Each of these instruments have their own accuracy parameters described on them, so you can consult with them as well.
Perfect. So we have concluded our Q&A period. The remaining questions, as I mentioned, will be addressed in the email on Thursday. Thank you, everyone, for joining us today, and we will see you next time.